Okay. Hello, everybody. My name is Carlos Sarmiento, and I'm going to be your teacher the following 4 days. Okay. As you know, the other teacher is going to be Andrea Schiffer, and as you know, the subject is called Water and Cooperation. Okay. Which are going to be the objectives that we're going to see here? Well, these are going to be the objectives. I will talk about the objectives, and then I will introduce myself. Okay. We will understand the implications of the lack of access to water in the less favored communities, understand future challenges in relation with water, become familiar with technologies related to water supply in cooperation contexts, and we will be able to design gravity water supply systems, pumping systems, and free flow sanitation systems. Okay, I know that 7 of you are from the water master and 2 of you are from the. All right, but we are going to, at the end of these 4 days, maybe now you think that it's going to be too difficult to be able to design water supply systems, but you will be able, because we are going to do it in a very easy way. We're going to do it with graphics and not with formulas, and you're going to understand it and to do it, not only to do it. All right? Even you that are not very familiar with water, maybe, but I promise that you will do it, right? Okay. As I told you, my name is Carlos, and I am civil engineer. I studied near here in Universidad Politécnica de Madrid. And then I studied in Torino, the hydraulic specialty. Well, when I started to work, I started to work in WASH projects. What's the meaning of WASH? I'm going to say this word a lot of things during these days. Okay. So a WASH project is a project in water, sanitation, and hygiene in a cooperation context. Okay, so in Spain, it's not possible to become a WASH expert just going to university. No? You can become an engineer or whatever, but there are other countries where you can study for being just a WASH expert, right? In Spain, we have a master in Universidad de Alcalá, near Madrid, and we have this subject in EOI. So you are going to be more or less a small expert, a mini expert in water and sanitation. Okay. So when I started to work, I started to work with some NGOs in the field, and I was working in. During these days, I'm going to tell you a lot of my stories about my projects and so on. So I was working in Honduras, in Paraguay, in Nepal. I was working also in Africa. And then maybe 8 or 9 years ago, I decided to look for a work here in Madrid for family reasons, because having a family, being the whole day abroad, is not so easy. So I decided to work here, and I found a job in Canal Isabel II. That is the company that is in charge of the water cycle in Madrid. Okay. So I started doing projects there. I was designing water projects for 6 years, and the last 2 years I've been in the construction area. So I've been designing, and now I am building all these projects. Okay. So but I'm very lucky, because being inside this company that I work every day in Madrid, I've been working this morning. Okay. There is a branch that is called Canal Voluntarios, and we are very lucky because some of Canal Isabel II workers, we can be in cooperation projects inside our company. So how does it work? We finance water projects and we do something like 2, 3, 4 trips in a year to design and to make the construction of these water projects. No? So now I am still in touch with this cooperation work thanks to this Canal Voluntarios branch. So because it's not very easy to go on with the cooperation life being here in Madrid. So this is why I feel very, very lucky with what I'm doing now. No? So, and now maybe you are thinking, okay, and then you will tell me about after the break, no? Why water and cooperation? Why have you chosen water and cooperation? No? Well, and my answer could be because you never know. Maybe in next year you could be working in South Sudan, or you could be working in Honduras, or you never know. It's also a good option. Well, as I told you, you never know. Okay, so this is, well, what I'm expecting from these lessons is I expect you to make a lot of questions. So, so please stop me whenever you want. That's no problem, and it will mean that you are inside my lessons. I would like to share my passion for this water and cooperation work. I am very happy doing what I do. And nothing else. And the most important thing could be to change your mind. Maybe I'm sure that most of you know a lot of things about hydraulics and designing and desalination and all these things. No? But now, one of my objectives here is you to change your mind. And when we go to a cooperation project, to forget a little bit about what you have already studied here. And because sometimes, for example, a project in South Sudan, well, sometimes not always, a project in South Sudan is not the same than a project in France, in Europe, in Canada, in Belgium, right? So sometimes we have to forget about our engineer ideas, and well, you will see during these days what I'm talking about. No? So today, now the first hour and a half, I'm going to talk about water supply. Well, 80% of my time I'm going to talk about water supply, that it's what I call clean water, okay? And maybe 20% of my time I will talk about sanitation, so dirty water, okay? And then Andreas Schiffer, who will be the next teacher, he is going to talk 80% about sanitation and 20% about clean water. But he will talk about clean water in emergencies. I'm going to talk about clean water in a cooperation context, not in an emergency, but in a project where we have more time for developing it. Now I will tell a little bit about emergencies and so on. So, water supply, water sources. So where do we get water from in our projects? Then after the break, we will see the theory about the water situation in the world, water crisis and international cooperation milestones. Tomorrow we will start with, we will go on with water supply. We will study population, demand and topography, and we will do this case study about gravity and pumping. Today maybe it's not so practical, but the rest of the days we're going to do very practical things. We will use, as I told you, graphics, and we will use Google Earth. So if it's possible for you to bring your computer, and if it's possible to have Google Earth installed, it will be brilliant, okay? Because Google Earth, right? Because with this Google Earth tool, with graphics, we are going to be able to design water projects in all over the world, okay? So as I told you, maybe today is not so practical, but the rest of the days we're going to be doing practical things almost all the time, okay? In couples, in groups, and so on. And the last day, I will give you a part of the world. I will give you a population in Guatemala, for example, and you will take this population, and you will design a gravity system, a pumping system, and a sanitation system. Okay, with these tools that I'm talking about. But this is the general case study. But before that, we will see the urban sanitation networks. Sanitation systems according to urban context and free flow, right? So, so as I told you, let's start with water supply, okay? So, water supply. What are we going to see in this water supply? Well, today we will see the difference between development and emergency. We will talk a little bit about SPHERE project, appropriate technologies, water sources, probably water supply and sanitation. And this is going to be the rest of the days. Well, if you want, in the break, I can give you all the presentations in PDF, right? Okay. So, development and emergency. I'm going to be talking almost all the time about cooperation development, but it's important for you to know that an emergency help is a project oriented to save lives and to relieve suffering. It has a maximum of 6 months, and it's of course in disaster situations, right? The most important thing is to save life. The future needs sometimes are not so important as in cooperation development. With Andreas, you will study a lot of these emergency situations, and you will do a practice where you will treat dirty water into clean water in the garden, in the same way that we do it in emergency situations. Okay, and that's going to be very interesting. Then, between an emergency help and a cooperation development, we have the rehabilitation. For example, what we have now in IT. Okay, is after a disaster, after an emergency, we have interventions from 6 months to 2 years to rebuild to the previous conditions, right? And then what I usually do, what I always do, it's a cooperation development project that it's based on long-time interventions to improve people's lives. We take care of future needs, we take care of communication to communitarian participation, children and women, creation of local skills, and so on, okay? If you have any question, please go on. Okay, what is SPHERE project? Do you know what SPHERE project is? No? Okay, so SPHERE project is it's a handbook that is of humanitarian charter and minimum standard in humanitarian response. And who has done this SPHERE project? Well, it has been done by all or most of the all the most important NGOs and all the international organizations that are working in this cooperation world. Okay, it recognizes you can download the last one, the last handbook that is from 2011 in this web. It recognizes that those affected by disaster or conflict has the right to a decent life. Okay, and we have four sectors in this first project. We have water supply, sanitation, and hygiene, so WAS. Okay, we have food security and nutrition. We have housing, human settlements, and non-food items, and we have action health. And now you are thinking, maybe you are thinking, so how does it work? Okay, do we see the water example that we can see in this SPHERE project? This is an extract from the SPHERE handbook. For example, a minimum water disinfection in an emergency situation has to have a turbidity less than 5 NTU. Okay, or you have to have more than 0.5 ppm of chlorine. I mean, it's a series of minimums that you have to to have in an emergency. But don't worry, because we are going to talk a lot during this day about this sphere. Okay? This is what the turbidity and so on. Right. So, appropriate technologies. This is one of the things that I told you before about changing your mind, no? Our technologies, our technologies in a water project in cooperation has to be appropriate, okay? Especially appropriate. Why? This is, for example, this is an example that I had in South Sudan, where we installed a beautiful, and white wash basin, but it was white, and that was the problem, because due to religion facts, they related water white with death, and they didn't want to use it. So sometimes it's important to listen to people, to ask, to not just go there and install my beautiful white wash basin. Okay, this is just an example. Okay, this is what I want to say, what I mean when I tell about appropriate technologies. Another example that we had, for example, in Tanzania, we had an hospital, a hospital here, okay, and we had a place where we had a borehole where we took water from. So we were thinking that the best solution could be to install a solar pumping from the borehole, and then to install a pipe, all these 1.5 kilometers. So to install a pump system here, a solar pump system here, a pipe, and then to bring the water to the hospital. But then we realized that we were in a place where there were not spares, it was a good solution, a good European solution. But what will happen when the solar system or the pump will break in a place like that? I mean, it was far from it was something like 50 kilometers from a city. So at the end, what we did is we chosen a rainwater catchment system from the roofs, from the hospital roofs. We took the water coming from the water in the roofs, and then we improved some manual pumps that we had near the hospitals. So we improved the roof catchment, and we improved these manual pumps that they had near the hospital. So of course they don't have right now water coming from a pipe. They have to work for a while and do the pumping, but it's going to be, in my opinion, more appropriate, because it's going to be maybe for 20 or 30 years, and not for only 2 or 3 years. It's going to be the time that the solar system is going to work. Okay, so that's what I mean when I talk about appropriate technologies. So usual questions to be done: what will happen if the pump breaks? It's important to ask yourself this question. And when I design a project here in Madrid, I never ask this question, of course. What will happen if the pump breaks here in Madrid? I will go to a shop, I will buy one. Okay. Where can I find spares? Pay attention in remote areas like this project that I saw you in Tanzania. Is there an easy maintenance? If it can be done by the community, much better. Okay, if the community can do the maintenance, it's much better. And for example, a manual pump can be maintained by a community because it's very easy. Another example, in Sudan, chlorine is not accepted due to the war, because they have fear to be poisoned. So sometimes, see, if chlorine is going to be one of your solutions, it's not to be accepted, so it's not to work. It's not going to work. So you will have to think in other options. For example, a filter, or whatever. We will also talk about that. Filters, chlorine, all this sedimentation, all these things. Okay. Well, here I say use your talent to find solution. It's a funny photo where, as you see now. So we go on with this appropriate technologies. This is a this is a school in Bangladesh made with wood. I like the example because it's because the wood has been taken from near the school, and it's very beautiful. You don't need it to be made with concrete or with iron. It's made with wood, and it's, in my opinion, it's beautiful. Okay, and it works. This is the school, right? So, water sources. So, what is water supply? As I told you, water supply, it's what we call clean water. So the water that we are going to drink. And we arrive to a place in an emergency context or in a development project, and the first thing that we ask is, where do I get water from? Okay. Nothing better. I say nothing better than asking people from the place. This is something that maybe is not written in the books, but it's the first thing that you have to do, is to ask people, right? And we have all these options. Okay, we have springs. We have boreholes, just deep boreholes. A borehole is a deep well. Okay. Then we have wells, that it's a small borehole. Okay. Here is the water. Then we have surface water, like in rivers, lakes, dams, or whatever. And then we have rainwater from rainwater catchments, as I told you of my example in Tanzania. Okay, so and then we have groundwater and surface water. So talking about groundwater, we have spring catchments that could be concentrated or diffuse. Now I will explain what does it mean. We have wells, traditional, excavated, manual drill, boreholes, infiltration gallery. I will show you photos from all these examples. I will show you photos for all these technologies, okay? So when we talk about groundwater, as you already know, we have more quality of water, because in general, groundwater has more quality than surface water, okay? That water in rivers and so on. Talking about surface water, we have streams, lakes, dams, ponds, and rainwater catchments, so with less quality of water. And now you can see here in this graphic, okay, in this graphic, that when we talk about, here we have the quality, and here we have the time for installing the technology, you know? So, for example, talking about a spring catchment, it has a very good quality and it's very fast to install a spring catchment. When we talk about surface water, the quality is not so good, but it's very fast to install these technologies. Okay? Then excavated wells, less quality and not so fast to install an excavated well because you have to dig. Okay? You have to dig a lot. Then talking about rainwater catchments, the quality is half-half, and of course the best quality you find in boreholes, but you have to install a borehole. You need a very sophisticated machine, and you need a lot of money. Okay, so the Sphere Handbook also talks about selecting the source of supply. And what does it say? Well, it says something very general, that you have to have amount available, and you have to be careful with the environmental impact of water sources. Okay, So it's important the proximity, sustainability. If you can choose groundwater sources, are preferred that, as I told you, than surface water. Well, the maximum distance of any home with the nearest water supply point is 500 meters. It's what SPHERE project says. Okay, 500 meters is the maximum distance of any home with the water point. Okay, now, so I will go on with all these technologies. And I will show you photos also from all these technologies. Okay, so a spring. What is a spring? A spring is a place where underground water surface, usually on the side of a hill or a mountain. And we are talking about, when we talk about the spring, we talk about groundwater, so the quality is quite good in general, because there are some springs, not maybe 5 or 10% of the springs, where the stone is not, or the water has not been filtered because the stone was, or the rock was fractured. Okay, so a spring is very good talking about quality, because the water has been filtered by the sun or by the gravels or whatever. But sometimes you have to be careful, because it could not be so pure. Okay. So the big advantage of a spring is that the water has been purified, as I told you, and generally it doesn't need treatment, so it doesn't need chlorine. That's good, as I told you before, because in some places chlorine is not accepted, and if you don't use chlorine, it's a good option, because if you use it, you need somebody who knows how to use it, so who knows the doses and so on, right? So we have two types of springs: concentrate ones and diffuse. Okay, so this is a concentrated spring catchment, but it's the normal one that maybe all of you have in your head. Okay. It's called spring catchment or a spring box. So maybe in some books you can also see that it's called spring box. And we have 3 parts, as you can see in the graphic. We have the sedimentation chamber, that is this part, and it's the place where water appears and we catch it. Okay, it's different in concentrate and diffuse one. So this part is going to be the difference between the concentrate springs and the diffuse springs. When are we using concentrate or spring catchment or spring box? We are using it in concentrated springs. So what is a concentrated spring? It's a spring where the water comes in a point. Okay, not in an area, but in a point. The water is appearing just in this point, in the mountain. Okay, then you will see the other example. So the storage chamber is this one. It's the place to harvest water. Okay, water gets into the pipe system from here. So from this chamber we will have pipes where the water will come into the pipe, and it will go till the tank, or it will go till the fountain, or it will go till the population. Okay, and then we have the dry chamber, where we are going to install the valves to open the pipe or to close the pipe. So these 3 parts, right? Is it clear? Are you already an expert in spring box? Not yet, no? But do you understand it? Mm-hmm. Edward, no? Yeah. Is it clear? Yeah, I think so. So this is a concentrated spring catchment. So this is we have this spring box, as you saw before. And then we have simple walls. This is a simple fountain. Okay, a simple fountain in the mountain where you where you take water from. It's just, here we have the aquifer. We install a wall with a small pipe, and here water is always coming. Well, not always. Always that we have enough water in the aquifer, okay? So we have simple wall and spring box, as you saw in the one before. Spring box is this one, okay? This is the chamber, and this is the simple wall, okay? The aquifer is here, and you have the fountain there. And this is the diffuse spring catchment that it's used when the water is not just in a point but in an area, okay? The water is coming in an area. So what do I do? What I do is I open a ditch, I install a pipe with holes, okay? A pipe with holes. And then after this pipe with holes, I install another pipe without holes, okay? Till the chamber. And then we have the dry chamber. So this is the same than the other one, but instead of having this small chamber that we had before, we have this ditch full of gravel and sand with this pipe with holes. Now you can see the example, right? I'm going to do the holes in the up part, not in the down one, and then from this pipe with holes, we will have the normal pipe till the chamber, right? This is clear? So these are the technologies that we use talking about spring catchment. This technology is one of my favorite. So if you could, and if it's possible, installing a spring catchment, it's brilliant because it's very easy to do it. The water quality is going to be 90% of the times very good. Yeah, tell me, Edward.
Is the holes always that small?
The holes are going to be...
Or can that depend?
It depends. Depending on what? Here, okay, you're going to install it in a ditch, right? So it's important not to install it with, for example, with sand, because if the sand is very small, it will come into the holes. Yeah. So depending on the material that you're going to use in the ditch, you can't do the holes very big. So if you're going to use, for example, gravel, that it's something like this, no? So the hole has to be smaller than the material. But as big, if you do very big holes, it's going to be good because the water is going to go very fast. And so depending on the material that you will use, the hole has to be one side or the other, right? Good question. So, as I was telling you, spring catchments are a very good option, in my opinion, because it's not very expensive. It can be done by the community, because at the end it's just making a chamber, and the water quality is going to be good. So it's a good option if you could, but it's not always possible because you have to have the possibility of a spring. For example, now I'm doing a project in Cameroon, and the only way of finding water is going very deep, and for going very deep, you need a borehole. So there's no option of springs. But if there are options, like if there is an option like a spring catchment, just think about that. Okay. And for example, in Madrid, we don't think about spring catchments because we are talking about a lot of water for a lot of people. I mean, we need to give water for 7 million people, and we will have to do millions of spring catchments, okay? So, but it's a very good solution. It's a very good solution for small populations, right? Traditional well. Well, a traditional well is a hole made. It's very similar to the springs, no? But the normal thing, for example, in Africa, is just to make a hole and to take the water, like in these photos. There is a moment, there is a time in the year where this hole will not have more water and it will end, and it's the way that the traditional wells work. But what I recommend is to protect these wells. Why? And what's the meaning of protecting these wells? Well, if, for example, this one is not protected, and this neither, no? Protecting the water means to install a chamber or something like that. I think I have something like this, no? This is a way of protection, just to install a little bit a small well made with stone or with concrete. And why? Why I was talking about protecting? Because first thing, because of the animals. Because the animals, of course, they need to drink water, and they will go there, and they will, sometimes they will, you can have contamination because of that. They will sit near the water, and so on. If you don't protect the water source, you can have manipulations, okay? Sometimes when we install these protections, sometimes or most of the time, we install some kind of filter, some kind of gravel, so we have more filtration in the source, so more quality. And the open sources has the problem with mosquitoes, because mosquitoes means malaria, malaria means deaths, and so if you can protect a traditional well, just do it.
So is this the technique that's used the most compared to the previous ones we've seen?
Again?
So is that the traditional wells, is that used in most of the cases compared to the others?
Yeah.
I think that's probably the easiest solution.
This is an easier solution. So if you can install a spring catchment, it's much better to install a spring catchment than a traditional well. But sometimes,
You need the water, obviously.
yeah,
You need the water to install the spring catchment.
yeah,
Whereas this, you just dig a hole and then you collect
Yeah.
the water.
yeah, that's the point. What's the problem of a traditional well? Sometimes that maybe you only have water for 2 months or 3 months because a traditional well is made digging, no? How deep can you dig? How deep can you dig? Depending, no? I've seen maybe 10, 12 meters, that it's a lot, but the normal thing is 4 meters, that it's a lot. So I try to dig 4 meters and now I'm in my house here in Madrid. I live in a small village. I'm trying to do a traditional well. And I've been digging for 1.5 meters, and I've been for more than 2 months. So it's not so easy to dig, okay? But yeah, it's like another technology. Yeah. So yeah, you can see here some photos, traditional well. Then I will show you at the end of all these sources. I will show all these technologies. I will show you more photos, okay? To see all the technologies at the same time. Excavated well. Well, the excavated well, it's similar to the traditional well, but going a little bit deeper, okay? So it's going to be dig by hand, but using some kind of protection and so on. So talking about this, I've seen only one time. I've seen one made of 20 meters. But of course, the advantages are that you can store water also in the well, because it's going to be huge, not huge, but it has to be maybe at least 1.5 meters of diameter, because you have to be here inside digging, so it has to be big. It can't be like this, all right? The excavation can be done by the community, and the disadvantages is that it's not very deep, and you have to be careful during the building, during the construction, because it can be dangerous. It can be very dangerous. And at the end, who is going to be the ones that are going to dig here? The children, because you have to be very small to be inside of the hole. So, you know. So not my favorite, okay? This is a manual drill well. A manual drill well. It's made with tools, but not with sophisticated machines. It's made. Now I'm going to show you now a video of this manual drill well for you to have it in your mind. Well, but the advantage is more efficiency. The work can be done by community, but you have less storage volume and more tool cost. It's not going to be very big, okay? The diameter is going to be like that, maybe 20-30 centimeters. And now you are thinking about, how is this tool? I'm going to show you this tool, because maybe it's not so easy to have in your mind. The music is. So they are digging the pit for the drilling liquid. Now you will. In the beginning you are not. Maybe you are not understanding everything, but at the end you will, right? Now they are installing the tower for the drill tool. This is in Bolivia. Nothing special. This is a manual pump, okay? Now you will understand why are we going to use a manual pump. Because I have a hole here and a manual pump. And now you are thinking a very small hole made by hand. Maybe now you are thinking why this hole? Okay, you will see. You see this manual pump? Hup. Okay. I install a pipe in this manual pump, and now I'm going to start the drilling. Okay, I'm going to drill with this tool. You see? You see, with this movement, the pump injects muddy water through the hose, passing the handle down the drill, steams to the drill bit where it comes out. So we have this hole with mud. I'm taking the mud from this small hole with the hand pump, and at the same that I'm drilling, at the end of the drill, of the tool, the mud, it's helping us to drill. Do you understand? Do you understand it? Okay, you see? I'm drilling not only with the impact, but also with the arcilla, with the mud, right? That is coming from the hole. And the mud then it's coming again to the hole. mat is made with soil and with water. Okay? The density is very important. And I need this tower. Now you will see why. I need this tower because I'm going deep and deep and deep, so this is why I need this tower in order to go on drilling. So when I finish, this one, I have to put another bar, and this is how it works. He has installed another bar and he goes on. You see? It's more and more difficult, you see? And this is the end. Well, that's it. That's it. Do you understand the process, right? So this is what we call manual drill well. Okay. Okay. So and then we have a borehole, and of course, one of the advantages is the excavation efficiency, but you have the cost. And you need external machines, and it's usually very expensive. And of course, there are some places in the world where you can't find a borehole machine. Okay. Well, maybe this is also interesting. How does a borehole works? You have here. You have made the excavation of all these. Okay. And you normally install a pipe here, okay, a pipe, in order so that the aquifer will not fall down. So you have a pipe here, but you need to do holes in the pipe so that the water will come into the pipe. And here you have the pump, okay, where we are taking the water from the pump with another pipe till the surface. Okay, so we have one pipe here and another pipe from the pump till the outside, right? Well, some of you already knew that, but anyway, no. Then this is also very interesting. It's a groundwater dam. Yeah, I'm sure that you have never seen something like that, because it's only used in some places in the world. Of course, you know what a dam is. Okay, a surface dam. We install a wall and we take the water from a river, so we made a lake and so on. But we are going to do it inside the ground. So we are going to drill. We're going to dig a very big ditch. Okay, we have here imagine that we have a gravel aquifer, and here we have, for example, granite. Okay, so this is here we have the water level. No, not yet. Imagine that we have here the water level. So you dig all this big ditch, and you install here like a dam, but inside of the ground. You can make it with concrete. You can make it with mud. That is the normal thing, with clay. So that the aquifer level goes up, and you have like a storage, a water storage, but inside the ground. Advantages: the quality of water. There is less evaporation, because in the dams you have evaporation and you are going to lose water. But it's very complicated to do one of these groundwater dams, because you have to dig a lot, and it's important. And it's sometimes you can have a problem afterwards. Imagine that you have a spring catchment after the dam. If you install this groundwater dam, maybe you are going to have the spring catchment dry. So you have to see all the situation, not only just to go with I'm going to install a groundwater dam, but also to see what it's going to produce, right? Do you understand this? Okay. This is not very common, but it's it's curious. Okay, so then we have an infiltration gallery. For example, when we have a river, imagine that you have a river here. Taking the water from the river sometimes is not such a good idea, because it's not so clean. But if we do here an excavated well near the river, okay, we can do an excavated well, and to connect the river and the excavated well, we can do an infiltration gallery that it's made with a pipe full with sand and gravel, so that you are taking the water from the river into my excavated well, but it's going to be filtered and it's going to be with more quality than in the surface, than in the river. Okay? All right. So, and then we have the river or stream catchments. Of course, sometimes it's the only option that we have, and the only thing that we have to know is that, and we have to pay attention, is to the quality. Okay. So sometimes, of course, for example, here we have installed a channel. This is the river. We have installed a channel, and then we have a sedimentation chamber, where that is nothing more special than a swimming pool. A swimming pool, or a place where the water is going to lose velocity, and the particles are going to go down. So I'm going to clean my water, just putting the water into a big swimming pool. So a place where you slow the velocity. Do you understand that? Tell me.
Given what you said about potential contamination, why would you cover this one as well?
No. I mean, you are just solving the problem of solids, but then you have to clean more things that you have in the river, right? Imagine that you have a lot of cows near the river, so and you have in the river you have particles, but also fecal contamination, and this is not going to be solved with the swimming pool. That was your question, no?
Yeah.
So it's going to solve some problems, but not all. Right, so this is a river or stream catchments. This is very common in Africa. It is called hafir, birkat, or pond, depending on the place. There is not an English word for that, so it's, well, pond maybe, pond in French. Okay. What is that? It's an artificial lake. Okay, for example, in some places in Africa, it's very common to have water, but only 2 months in a year. So we make a big swimming pool, a big lake, just digging in the places where I know that the big rivers are coming in the rain season. Okay, in the rain season. So during the rain season, it's going to get full of water. And we normally use this water they normally use this water for cows, for animals, and so on, right? But sometimes there's not other option, and they use it for drinking. We try to install house filters and chlorine systems and so on, so that you can clean this water. But it is curious because sometimes, so in 3, 4, 5 months, it will get dry, and you're going to have there a lake without water. So what people will do is they will go there, and they will dig, and they will go to look for the water. And you can see like the lake with small holes, because made by people looking for the water. And that water is going to be better than the one in the lake, because the water that is groundwater is going to have more quality. Tell me.
So I think a pond, the water's still, right?
Uh-huh.
The water doesn't move.
Yeah.
So that attracts loads of diseases and bacteria and stuff like that.
Yeah.
But that may be not like a very good solution.
No, but sometimes it's the only solution. I'm just showing it, but no, of course it's a good point of view. It's not a very good solution, but sometimes it's the only one.
In what context would that be the only solution?
Well, in a contest, where have I seen this? No, that's a question.
What were the contextual elements?
Well, I've never done it. Okay, but I've arrived in some places where it was done. And which is, for example, which is my solution in this contest? My solution is, this is a good idea, no? But for animals. What I will do is I will install excavated wells here, and infiltration galleries, for example. No? It could be a solution, so that you can clean the water from the pond till my excavated well. So maybe it's not a technology that I will use, but it's a technology that exists. Yeah, that's the point. Because as you told, we have organic material, and you need annual maintenance, because it will get full with solid particles. So at the end of 5 or 6 years, you will not have lakes, so you will go on digging and digging, and so on. Do you understand? And then, again, no? This is a very good example with talking about your question. This was in Tanzania too, okay? This photo. I reached into this population, into this village, and I saw this photo. The girls taking the water from the river, and the cows drinking from the river, and a lot of people with diarrheal problems during the year normally. And it's clear, and you don't have to be an expert for knowing what is happening here. No? So what we did here is we did what I told you before. We did these excavated wells with an infiltration gallery and with a manual pump. So at the end, they had this more quality of water, and the cows will have different places for drinking. And of course, my excavated wells has to be protected.
So prior to the introduction of an excavated well to have a separate water source, would the local residents boil the water before the consumption, or just
boil?
Yeah, like to kill the bacteria.
Yeah, in some places it's also a good option, but the problem sometimes is how do you boil it? No, you need the energy to boil it, and sometimes it's not so easy to. But yeah, boiling is. You will also see with Andreas. You're going to see a lot of things about treatment, chlorine, boiling, and yeah, it's a.
But is that part of their mindset then?
Sorry?
Is that part of their mindset? Are they aware, like certain of these communities, would you say they're aware of the effects of boiling water?
Yeah. For example, here, well, I've been in some contests where it's a very good solution, and you don't have to change their mind because they have been doing that for a lot of time. But because they have they can do it in a very easy way. They have the energy to do it. But in this contest, it was not so easy to change their mind talking about boiling, and it was not so easy to talk about chlorine. So it was very difficult. No chlorine, not boiling, and no, that was why we decided to do this filtering. So in a way, at least you have it filtered, and we reduce a lot children deaths with doing that. But of course, there is not a super good solution. No, you have to see a lot of things. No? And that's also the beautiful things about these projects, no? Because in France, in Italy, in Germany, all the projects are the same. I'm going to take the water from the dam, from the river. I'm going to install a water treatment plant that's going to have a sedimentation, a filtering, and so on. It's always the same, no? And we are, I mean, you are from Belgium. Okay, so and we are very similar. I mean, so, I mean, you don't have to convince myself of using chlorine and so on because no. Okay, so that's the good thing. And then rainwater catchment, another technology, but it has also problems, no? So we are going to use the roofs for taking the water from the roofs. Advantages: the water volume. Disadvantages: the first floods contamination. Sometimes the roofs are dirty, so in the first floods is going to have contamination. So I have to be careful. Sometimes I'm not going to take the first flush, but I'm going to take after a while. And demineralization of water. This water is not going to have mineralization because of for example, because of being in an aquifer, no? So what we usually do is we take this water into a tank, and then we will use it. But of course, if I don't have rainwater, I'm not going to use my rainwater catchments. So it's going to be a good idea when we have water during the whole year, more or less. If not, I will have to find other solutions in this dry season. Okay, now I will show you some photos. Okay. Photos. So we'll see some boreholes. This is a borehole we did in Argentina. You see the machine is not so easy. You need you see. This is a borehole, okay? But this is curious because it was a borehole made in an excavated well. You see? First we had an excavated well, and as it was in 1 month and a half or 2 months it was dry, so we decided to go deeper with a borehole. With a borehole you can go 80, 90 meters deep, no problem, 100. So that we could go to a deeper aquifer and to obtain more water, okay? So boreholes, more photos. Dams. This is a dam we did in, this is very curious. This is a dam we did in Ethiopia. We only with 60,000 euros. 60,000 euros we did this dam. What we did is similar. We built this dam for animal consumption, and then near the dam we installed some manual pumps so that we obtain clean water from the aquifer made by the dam, and we had water for the animals that were very important for the population too. Okay. Ethiopia dams. This is nothing special. Only for you to see that normal ditch with a plastic pipe in 2 days you will be designing these pipes, okay? And for you to have these pipes in your head, plastic pipes are the normal ones that we use in this context, okay? Excavated well, excavated well. Nothing special. This is the one you saw before. What else? Lakes. Well, as you saw before, this was the one that you saw. Lakes. Lakes. The girls. The lakes. Using the bikes for carrying the water from the lake. Okay. What else? Manual pumps. Well, there are a lot of kinds of manual pumps that we will see on Thursday. But for you to have a manual pump in your head, this is okay. It's important also to protect sometimes the manual hand plays. The drainage also. Okay. This is a manual pump. Rainwater catchment that we did in IT. We were taking the water from this roof and we were using this tank for storing this water. Here, this is a filter. And let's see, this is a filter, so before getting into the tank, we had here a small filter with sand, a sand filter, okay? So before getting in the tank, we have a filter. The same. What else? River catchment. That's very interesting. This is a river catchment, no? As we saw before, a way of catching the water from a river is making a channel, no? But it's not so easy to install a channel with a river like this, with this quantity of water. So first thing we have to do is to install or to build a dam, an artificial dam, you see, so that we change the river way.
Is that built? What are those? Yeah, sandbags then.
Yeah.
Is that what you drop in the water?
Yeah.
Is
Now,
it always the same case with sandbags?
sorry?
Is sandbags always used?
Well, I have done it only twice in my life, and I've used always sandbags.
Okay.
It's a very good option, very cheap. But now you will see why. No, maybe now you are thinking another thing. Let's see the rest. Look, sandbags, right? But what am I doing? Okay, I'm going to install a channel. So I'm building it. Okay, here I am building it with concrete. Here I have the bags, so I can be working here because I don't have water. Now I am doing like a small dam, so in order to get up the river level. Okay, now let's see. Now here you can see the situation, no? The water is going in this direction. I am doing this small dam, and now the rainwater catchment will start here. The rainwater catchment starts here, and it will come into a channel, and it will go to the village. And now here you can see it. So what we have done is we have here, you can see the river. The bags were here before, so we have now the river level is a little bit upper here because we have done like a small dam with concrete, so that we are taking the water into this channel like this. Do you understand? Yeah. So all these photos that you have seen with the this is the dam, okay, and the last one is this rainwater catchment, right? Okay, here, yeah.
This is river water, not rainwater.
River water. I said rainwater, river water. Yeah, thank you. More photos. Yeah. Yeah, river catchment. Setup. And this is a treatment plant that we usually use in emergencies, where we can take water from rivers and purify it to water like this, okay? So we have a filter, a sedimentation chamber, a chlorine machine, we have everything there. But it costs 40,000 euros, each one of these. And you are going to do this practice with Andreas, where you are not going to do the treatment with this plant, but you're going to do the treatment in a very easy way with with small swimming pools, like swimming pools for children, with plastic swimming pools. So I mean, what we want to show you is that you can do these emergency treatments in a cheap way, in a cheaper way than using these treatment plants. The treatment plants are a very good option, but you have to pay for them, and you have to take them into Pakistan. You have to take them into Morocco, whatever it is, South Sudan, and you have to put them in an airplane. It costs, and sometimes you have to cut them because it's not very easy to find an airplane for such a plant. So you will see other options for treatment. Maybe not so sophisticated and not so, but very good at least at the end, no? Sometimes you are spending here 40,000 euros. Maybe you can make this batch system for I don't know, for 1,000 euros. It's called batch system. Okay, the one that you will practice with Andreas. You will do the treatment. Okay, and you will have to drink the water. So, more photos. Spring catchment. Spring catchment. Well, this is storage chamber. This is the first chamber that I tell you. Okay, that I told you. Nothing special. The spring catchments. And traditional wells. Okay, not protected. These one are not protected, all right? This one, yeah. Okay. So.
Is the water further purified or filtered from when you take it from like the traditional well that's been enclosed?
You mean how are we purifying or filtering this water from a excavated well?
Yeah, because just because it's covered doesn't mean that the water is devoid of contaminants.
No, because you can see this one, for example. This one, you are just covering the water. That's the only thing that you are doing. You are just protecting it from the animals, and that's it. But what you can also do, imagine, is not this example, right? But what you can do, it's you can excavate a traditional well. I don't know, 3 meters, and you can do it with, I don't know, like that. And it's important to have holes here, no? But here you can install gravel or gravel and sand, so that you can do a filtration, an additional filtration. Do you understand? So this is why it's not this example, but it's a more sophisticated excavated well. And so you have the protection and also the filtration. And how do I get water from this excavated well? You have some options. Just with a rope, no? Or even with a manual pump, or with a Mecate pump, all these pumps that I will show you on Thursday. But if we are talking about 3 meters, you can use a lot of manual pumps that you will see. Okay. So now I want to show you. I want to talk about a very important thing. It's the differences between water supply and sanitation. This is pay attention here, okay? This is very, if you understand now what I'm going to tell you, the following days, the designing of all these days are going to be very easy, okay? Maybe some of you know it, but it's good to listen to that again. So what we usually have in water supply, so in clean water, when we talk about clean water, it's a pressurized pipe. So it's a pipe full of water. For example, the pipes that we have here in the bathroom, or the pipes that we have here in the garden, if we take one of these pipes and we break one of these pipes, the pipes are with pressure. So imagine that we make a hole here. There will be a water column as high as the pressure that we have here. So if we have, for example, 7 bars, okay, it means that we will have a column of 70 meters of water. So, more or less, it's a very simple way of explaining it. But so it will mean that we'll have a column of 70 meters. Maybe it will not be so high because of other reasons, but there will be a very, very big water column because we have it pressurized, okay? So this is what we use for water supply. Why? First of all, because we avoid it from external contamination. So if you break one of these pipes, it's impossible to contaminate this water because we have more pressure inside than outside, because outside we have atmospheric pressure, so the water is always going to go out. So it's impossible to contaminate it. The other and very important thing is that when we have it pressurized, we can go down and go up hills. So if we have a tank here and my pipe do this till my house, you don't see it, no? I'm going to. So if I have a tank here, my pipe is like this till my house. If it's pressurized, okay, it will go up and down because my tank is upper than all these points, okay? This is the good thing about having it pressurized, right? And then we have the the dirty water. Or the channels. Sometimes we have channels with clean water. You know, a channel is not a pipe, but it's something like this, for example. Okay, it's an open pipe. So when we have a channel or a dirty water pipe, it is not pressurized normally. In general, it's not pressurized. So what it means? It means that if I break the pipe here, the water will not come out, because I have the same pressure here, because here I have air than outside. Okay? So the good thing about this is that it has not to, we don't need it to be very, we don't need a very big pipe. It can be maybe 1 millimeter. You don't need very big thickness, right? But talking about a pressurized pipe, you need to be very big, because you need it to suffer a big pressure. So I'm going to pay much more for a pressurized pipe than for a sanitation pipe. Okay. Well, the bad thing is that if we break this, it can be contaminated by sometimes some things that we have outside. But in general, it's going to be dirty water that is going to go to a treatment plant or to another place. So I don't care so much if it's going to be contaminated or not. Okay. But the bad thing is, imagine that we have a channel. If we have a channel here, the channel will not go up hills, and that's very important, okay, for the designing and so on. So the channel, well, this is called free flow systems, and these ones are called field systems or gravity systems or pressurized systems. Okay, free flow, when we have air inside the pipes, when we have atmospheric pressure. Okay, and this is very interesting when we see the next one. For example, this is here in Madrid, in Patones, where we take water from the mountains to Madrid. Okay, so we take the water from the big dams in the mountains, 80 or 90 kilometers from here, and then we transport this water till the big tanks that we have in the city. All right, and the ones that came before, they installed here the down channel, canal bajo, it's called in Spanish, and they didn't know about these pressurized things and so on. So they did a channel, and they had here like this valley. So they built this bridge in order always to go down, because they had a free flow system. You need always a slope in order to go down till Madrid. But then they installed, after some years after that, they installed the Canal Alto, okay? And the canal is coming here, and they had a problem because they need to go up. So what they did is, here we have channel. Till here they had channel. Okay. Then after the channel we have like a swimming pool here, and it's something like this. Channel till here, and then like a big swimming pool, and then pipe. Okay. Here we have channel like this, then swimming pool and a pressurized pipe. So the water goes down, goes up, and again I have a swimming pool here, and again it will go on with free flow, like a free flow system. Do you understand the mixture between free flow system and pressurized system? But this point has to be lower than this point, because if not, the water will go in the other direction. All right, Edward, it's okay? 50-50.
Could you just repeat that swimming pool system?
This one.
Yeah.
This swimming pool is here.
Yeah.
Okay, so we are coming with a channel like this, with a free flow system. Well, the real thing is that it's covered, not for it not to be contaminated, right? But with free flow system, because making a pipe for all these kilometers was very expensive, no? So when we reached this point, they realized that doing a channel till here,
It's not going to go up.
okay, so they decided to put a pipe, okay, a pressurized pipe. So from this swimming pool, you change from channel to pipe. And then again, in the other swimming pool that you have here in this house, you return again to the channel system. It's okay?
Yeah.
And that's important because of your designs, because of the designs that you're going to do these days, because you're going to design gravity systems like this. You are going to design free flow systems that we normally use in sanitation, in dirty water, and you are going also to design pumping system. So what happens when we have water here, and we want to give water to this house? We have to use a pump, and you are going to be able to design this pump. Maybe you already know that you will do it with another point of view, okay? And you have to be able to go to the shop and say, I want to buy a pipe. I want to buy a pipe, and I want to buy a pump, because they are going to ask you. Because incorporation is like this: you are going to be the one that are going to do the designs, and you are going to be the one that are going to go to the shop. And they're going to ask you, sorry, but which pump do you want? And you will answer the question. I want this pump. You will see during these days. Okay. If this is clear, all these days are going to be brilliant. Okay. So, well, and now I'm starting with gravity and so on. So, gravity flow water supply system. Of course, if you have now talking about water supply projects, okay, clean water. Forget a little bit about what I tell you about sanitation and so on, free flow. So I'm talking about water supply systems, about pressurized systems, okay? If it's possible, the best option is always to take water from, for example, from a spring catchment in the mountain, where I have gravity, and I can take the water from this spring catchment and take it into the village, going up and down and so on. That's the best thing, because there are not expenses, because I don't have pumping, so I don't have to pay for the electricity or whatever. The maintenance is minimal. The pressure in the system is controlled very easily, okay? And the systems are robust and reliable. So the best thing always is something like this, no? I have a mountain, I take the water from a spring, I go from this spring till, for example, a tank, and from the tank till the village. That's the best thing, but it's not always possible. But sometimes it is, okay? All right. But sometimes, what I do, for example, in this project that we did in Honduras, we had some boreholes in the village, because there was not a spring catchment and so on. So the houses were here, and the borehole that we did was here. Okay, and we installed some some water points in the village. Imagine that a child goes to this water point and he wants to have water. If it's impossible to have water all the time, only using a pumping system, because we will have to use the pump maybe 100 times in a day, and that's not very good for the pump. So the pump, it's better to use it at maybe 6, 7, 5 days, 5 times in a day, because if not, it's working all the time, working, not working, and it's not very good for the machine, right? So the best option, and it is a mixed water supply system, is to do what we did here. We have a mountain here, so we install a tank here. So we took the water from this borehole with the pump during 6 hours, for example, during the night. We were pumping the water from the borehole, fill the tank, we fulfill the tank, and then there was another pipe till the fountains that were pressurizing. The tank was pressurizing all the fountains during the day. So if you want to have water during the day, you will not have to be working the whole time with the pump. Do you understand, Edward?
No, I get that. I just don't understand why you're putting the storage uphill, up there.
Free flow.
Okay, yeah, so that I get, but is that not like doing twice as much work?
Yeah, you have to do more work in a way, okay? But it's not. This is very high. It was not so high. It was something like 20 meters, okay? And this was 150. All right? So instead of working the whole time 150, we were working only 270 once in a day. So and when the electricity was cheaper during the night, so that we were not breaking the pump in 1 year, but it was going to work for 20 years. And then during the day, we had it pressurized. Do you understand?
Yeah.
But it's a very good question, because maybe it's not so obvious to work a little bit more, but it works, because the very expensive thing here is the pump, and if you have to be changing the pump every year, okay. No questions? Okay. Well, this is what I explained, right? Then, population and demand. So, let's start with this designing part that we are going to do these days. The first thing we need to know when we reach into a place, of course, is to know where I'm going to get water from. Now you have seen all the technologies, and you are going to ask people, you're going to be there some days, and so on. The next question is how many people are here? How many people do I need to give water to? And that's not an easy answer. That's not an easy answer, right? Well, here I say a lot of obvious things that if you observe existing social structures and the collection efforts made in the past, you can get an idea of the organization that you have in the population. I'm talking about social aspects, no? Because here there is I don't know if there is an example here. No. Yeah, here, for example, to ignore the needs of a collective group can lead to resettlements and even sabotage of complete systems. No? Imagine, for example, that a water project uses almost all the available water, leaving farmers downstream with nothing. This is obvious thing, no? But as I told you before, it's important to ask where is the water coming from in this place, but also, do you want a water project? No, because sometimes it's something that we think that it's obvious, but sometimes it's not. So if you reach a solution, it has to be talk, and it has to be, everybody has to be agree with the solution, right? Or not, or if not everybody, at least almost all the population, right? So what I want to say here is not to ignore people. Okay, period on population design. Normally, we take 30 years for the period design, or 15 years is system that can grow easily. What do I want to say? For example, today, in a village that we were going to do the projects, there are 100 people, no? But am I going to design for 100 people, or am I going to design for, I don't know, 120 people that we're going to have in 30 years? No, that's not a very easy question. Which is going to be the period of population design? And these are some things that you're going to do tomorrow in a small exercise that we're going to do, right? So my advice is that for pipes I will use 30 years of period, and for tanks and pumps I will use 15 years. Why? Because a pipe, for installing a pipe you need to do a ditch, and for a tank or a pumping system, you just need a machine, or you just need a tank. So if in 15 years you need another one, you can do a pump and another one behind that one, or you can install a tank and another tank near that one. So for the pipe I recommend to use 30 years, for not to open the ditch again and install another pipe, and for the pumps and tanks 15 years, right? So the question is, and what about the current population? The population today, how many people do I have here? Well, we are going to use census, service, hospitals, Google Earth, and that's what we will do tomorrow, because this is something that I've done when I'm desperate and I don't have information. Sometimes you can go to Google Earth and to count houses. That's the last option. But if you, for example, sometimes if you have to do a previous project from here before going there, that's not the good thing, no? But sometimes, for having a number in your head, you can count houses in Google Earth. That's what we will do tomorrow. And that's, Google Earth has a very good tool that it's, you have a clock and you can see photos from the past. So you can see how many houses were there, for example, in 20 years ago. So you can see how the growing has gone all during these days, during these years, right? So you can use projection formulas. So if today we have 100 people, tomorrow we will have, we will use it tomorrow, no? Depending on the time and depending on the growth rate, you can know how many people were there. But for knowing this growth rate, so the projection that we have had all these years, we can use this Google Earth. But the best option is going to the place, asking people, seeing census, going to the houses, and maybe making the census yourself, right? You can go also to projects made in the past, because maybe you are not the first that is doing a project in the village. So just look for all this information. This is an example, for example, no, where we we have the current population is 3,780 people. But 5 years ago, there were 2,700. So what will be the population for a design period of 25 years, for example? But there are three formulas. We are not going to go very deep in these formulas, and we are going to use the arithmetical one. Okay, and the arithmetical one work with this. The final population, it's the population today, okay? And we use 25 years, that is the design period, and we have to use the growth rate. The growth rate is the percentage of the growth. Okay, we have these people today, and in the past we had this one. We have to obtain that we have 88% of growth rate each year, and that is simple. We will use this with this formula, the geometrical one, and that's all, right? I don't want to go deeper about that. Another interesting thing that we can do maybe tomorrow, because in 5 minutes we will do the break. Tomorrow, if you can install, as I told you, you can install Google Earth, we will start doing all these exercises. Edward is doing already, no? Yeah. For example, this is an example talking about the clock, no? The clock that I told you before. This is IT, this is for Fins, 1 day after the earthquake in 2010, right? 1 day after the earthquake, there was no people here. This area was not affected, right? This is 8 days after the disaster. People started to install here because there were no houses here. There was a place there was a free place here. So as you can see, that photo is 12 days after the disaster. You see, it's full of people, and here again, some months after that, it was full of people. So you can see a lot of photos, and imagine that you have to prepare I don't know, a manual pump or whatever, or a treatment plant for this area. At least you can have an estimation of how many people you have in the place, no? So this is what we are going to use tomorrow for knowing the growth rate of different parts of two examples. Some of you will do an example in Honduras, and some of you will do an example in Sudan, right? Talking about daily base demand. Now, imagine that now we have, and we already know number of people that we have, 2,000, and today the current population, and we know already the population in the future in 30 years. No, now we need to know the daily base demand. So the quantity of water that they are going to drink. So because I have to design, no. So I need people and quantity of water, and this is called daily base demand. It depends on a lot of things. So there is not a rule, depending on if it's Africa, if it's Spain, for example. We in Europe we use about 250 liters per person day. 250, okay, and 250. Talking not only about drinking, but also washing machine, the bathroom, and so on. 250. It's quite a lot. And the Sphere project says that in an emergency, the Sphere manual, in an emergency, the minimum is 15 liters per day. 15 liters per day. Why 15? The survival needs, drinking and food, 2.5–3 liters per day. The basic hygiene practices, 2–6 liters per day. And the basic cooking needs, 6 liters per day. So it's about 15 liters per day. If you compare it with 250, it's, but it's true that 15 is for an emergency situation. Now in development projects, that is the ones that we are going to design here, with pipes and so on, not with treatment plants, with fast plants, but with long periods in the time, we will go to 50, 60, 70 liters per day, depending on the place, depending on the traditions, depending on a lot of things, okay? For example, a student in a school if you have to design a school water supply system, a student needs 5 liters, or a cow needs 20 liters per day, or a rural inhabitant 30 liters per day, right? I like this graphic because it means that the minimum that a person needs in a day is something like about 20, 50 liters per day, right? If the water is in your house, you are going to use 70. But if the water is from 5 minutes to your house to 30 minutes, you will use always 20 because it's the minimum that you need. So it doesn't depend on the distance, but it depends on this number. I mean, do you understand the graphic, no? But of course, if you have it at home, you will use much more, right? So we have these numbers, and for the moment, I think it's enough. So yeah, with this, we have seen these technologies that we use in water supply systems. We have seen a little bit about population, and we have seen a little bit about demand. And tomorrow, we will obtain the profile, the topographic profile with Google Earth, and with the profile, the population, and the base demand, we can design our gravity system. Okay? Now let's take a break and see you in 30 minutes. Okay?